Welcome to lecture 21 of PDEs. In the first part of this lecture, we'll be looking at the Green's functions for the three-dimensional wave equation. Okay, so what we want to solve is the D'Alembert operator, which is basically your wave operator, which is the spatial Laplacian minus dtt over c squared of u is equals to a source. And the method we've been using up until now is we find the solution to the Green's function in the of the source point. So in other words, the D'Alembert applied to the second set of variables equals to a delta function in the spatial variables and a delta function in your time variables, where r and t represent the difference between the field point and the source point. Okay, and we're looking for, in particular, for the case where the Green's function is equal to 0, where t prime, that your source point is greater than your field point. In other words, we require causality holds. You have just to find r as the difference between the vectors of our source point and our field point, where we want to know the actual solution. Okay, and up until this point, and even with the next formula, we've been deriving the thing for the general n-dimensional case, and in particular we'll find now the specific Green's function during this lecture for the three-dimensional case. Okay, and furthermore we'll be finding the Green's function for an infinite domain, and when we do that, then we showed that basically if we find G that satisfies this condition in addition to this condition over here, in other words causality, then we can write down our solution for u of the above equation as the following integral expression, where the integral of the source or forcing function is over the previous time and the full spatial domain, that's the infinite Rn domain, plus a contribution from your initial condition and the initial time derivative of u that's specified. Okay, and so this is just the sketch. Here is P, the source, the field point where we want to know what our solution is. Here is Q, the source point, and we integrate over this whole domain, which is now, it has infinite extent, where T is less than, where T prime is less than T. Okay, and we're integrating over our prime coordinates. So we showed in, I think, 2 lectures ago, that in general, for the symmetrical solution for G, we can write it as G dash R, where R is the difference between the source point and the field point. In other words, the vector that points that way. And T is just the difference between your source time and field time. And we derive generally using Fourier methods that the symmetric Green's function in any dimension obeys this formula. And in the previous lectures, we've explored the formula for dimension 1 and 2, and the subject of this particular talk or lecture is the dimension 3. In addition, we'll also be looking at an example as how do you actually evaluate the Green's function once you have it. Okay, so in 3 spatial coordinates, the main thing we have to do, just as in the 2-dimensional case, is find an expression for this dnk. And we're going to be working in spherical coordinates because they naturally adapted to your symmetrical solution. Okay, so here we go. We simply have our Cartesian coordinates here, and our spherical coordinates are defined in the standard way, where rho plays the role of a radius. You have sine theta, which is your angle with your z, where theta is the angle with the z-axis, and so the projection of this vector onto your xy plane is then given by sine theta, in other words, that height, times rho times cos of phi, and sine of phi, depending on you doing it. And the projection of your vector onto the z-axis is just rho cos theta. So that's just that distance over there. And then we have our phi and theta in this sort of, with this domain. And in order to compute this integral, the dnk, we just have to apply the Jacobians. So we have d3k is then the Jacobians, the determinant of the Jacobian, and taking the square root of that, of this transformation. So you work out dx d rho, dx d theta, dx d phi, and similarly for y and z, and you work out the determinant of that, and you take the square root, and then you get k squared sine theta, and then it's dk d theta, sorry, d phi d theta. So this now becomes your volume element that you put in there. The remaining thing that we have to evaluate is this r dot k, and n is easy to substitute in there. So r dot k is simply r dot k can simply define as the norm of r times the norm of k times the angle between it. And if we have the freedom, because we're integrating over the whole domain in k, or the whole R3 in k, we can choose our axes so that the x-axis coincides with the r vector, and then it simply becomes r dot k is equals to rk cos theta. Okay, so that simplifies the calculation, and we can then express this whole integral given where r is actually just our norm between r prime and r. We can express this integral as the integral of from 0 to 2 pi, 0 to pi, which is just your domain of phi and theta, the integral from 0 to infinity, which is just your k's extent, and then it is k squared times sine theta. But if you recall, our Green's function that the integral we want to work out is 1 over k, so I've cancelled that out. So it's just k sine theta. And now we want to evaluate this integral. And once again, this looks very much like a Fourier transform like we did in the two-dimensional case. But if you want to evaluate this integral, it's actually easier to look at the theta integral first. So let's just rearrange this integral slightly. So there's no explicit dependence on phi, so we can move sort of the averaged angle in here. So it is the integral from 0 to 2 pi d phi over 2 theta. So this thing just evaluates to 1. Then we keep the r integral outside. So it's the integral. So we swap the order of, the k integral and the theta integral. So it's the integral from 0 to infinity of k. So the sine k, sine t ck multiplied by k is not dependent on theta, so we take that out. And then we're left with this integral from 0 to pi e to the I r k cos theta sine theta d theta, which is very, very fortunate because the derivative that appears in the exponent is down here. So you can actually easily write down the exact integral, and you simply get that the derivative of minus e to the I r k cos theta over 2 pi I r k. If you take the derivative of this thing, then you will get that integral over there, and we have to evaluate it at the boundaries, so it's at 0 and pi. And if we note that cos of 0 is just 1 and cos of pi is minus 1, and so we just put it in. And we can also see that the k that came out by sort of making sure that we have an exact integral, that k can now cancel with this k that comes from your original definition of your Green's function over there. Remember, the other k cancel. This k comes from the k squared over here. The other k cancelled with this 1 over k. So this now miraculously cancels out, and what we're left with is basically sine tck e to the minus I rk over 2 pi I r. Okay, r is not dependent on any on k, so we actually can move it out of the integral. In fact, this whole denominator we can move out. Plus this term evaluated at theta is equals to 0, so that is just e to the I rk over 2 pi I r. Okay, and note that once again we have something that we got in the one-dimensional case, very, very similar, except that we're now dividing by an additional term, an additional constant term multiplied by r. And we can do the same trick. We can write this integral that goes from 0 to infinity as an integral that goes from minus to infinity to infinity. And the way we do that is simply to note that if we change k to minus k, in other words, we start with a new variable k prime, sine of tck prime is just equal to minus sine of tck. Here the minus remains, so the two minuses cancel, and this term then is exactly equals to that one. dk gives you another minus sign, but your limits goes from 0 to minus infinity, so minus, so that will be from minus infinity to 0 of this term, and then the remainder one is you simply add that from 0 to infinity. So this integral up here is exactly equal to this integral down here. Okay, and this takes, we can expand even further if we expand sine in terms of its expression in terms of its exponent, or sort of exponent expression, and multiplying out, we get that this expression is equals to e to the 2k tc, that comes from sine plus r, minus e to the ik minus tc plus r. Okay, and you need a factor of 2i underneath, so 2i multiplying by this, we have 2 I times I gives you a minus. Okay, and this is very easy because this is simply the definition of a delta function if we take this 2 pi out. Okay, so the integral is reasonably easy to compute. In fact, it's often true that the wave equation in odd dimensions, the integrals are easier than the wave equation in even dimensions. And you can the method that we've used here, you can generalize to any dimensionality simply by having a slightly more complicated factor of d3k over here, or dnk. It becomes more complicated, but it's basically the same integrals we compute, and it's just that the odd terms are often easier to do, but you can always do it. Okay, so now here's just one thing. We have required that g should be equal if t is greater than 0. Okay, so if t is greater than 0, this term is not a problem because it always is 0, right? The delta function is only infinite at when the argument is 0. So this thing is always 0, but this guy is not. Okay, if t is greater than 0, it has the possibility that this thing goes 0. So we basically omit this part of the solution because we have this requirement of causality. Okay, so finally we get that in general, if it was a function that had supported more than 2 points, we would just multiply it with a step function, but here we can simply implement this condition by saying that we just omit this one. Okay, so here we have our Green's function that obeys the causality relationship. It's just simply a delta function at ct plus r minus c times 4 pi r. Okay, so now I'm going to do the similar thing to what I did with the two-dimensional case. I'm going to put this Green's function into this general expression for u and r, and I'm going to massage it even further to make the evaluation of this thing given a specific source, a specific initial condition, and time derivative of that initial distribution, just to make it clear how to go about evaluating those functions. Okay, so once again, I'm going to write the solution as u, which is equals to a contribution that comes from your source, a contribution that comes from your initial condition, a contribution that comes from the time derivative of your initial condition. Okay, and I'm going to evaluate each single one, and just for reference purposes, here's our Green's function written out with your your field and source points dependence being made explicit. Here's the one we derived in the previous slide, and here it is just written out as ct minus t prime and minus r minus r prime. Just note that the argument here I've multiplied with a minus sign to get from there to there. Okay, and the reason I did that is that this is always positive, so this delta function is only non-zero when the distance between the physical distance between your source and field point is equals to ct times the distance between your source and field time. Sorry, your field and source time. And here's the 4 pi r that's in the denominator. Okay, so when we evaluate this, we have to work out those integrals over R3 of various combinations of this function g. And to do that effectively, because we have written the Green's function in terms of r, and so the only thing that enters is the difference between r and r prime, and you're integrating r prime. One way of doing it that's convenient for most methods of evaluation is let us choose the origin of the spherical coordinate system in R3 to be r. Okay, so we did this in a 2-dimensional case, and we'll be doing it again here. And if we do that, we have the source point is simply r prime is equals to r plus this vector r, which is basically the vector from our origin to the source point. Okay, and we can write r prime then as r plus the norm of r times s, which is now the unit vector in the r direction. Okay, and if we do that, our forcing term, we can basically evaluate it as the integral from 0 to t dt prime, the integral from 0 to infinity times r squared dr times the integral from 0 to 2 pi d phi times the integral from 0 to pi sine prime d phi prime. Okay, and here's our Green's function. What I've done here is use that rule for rescaling the Green's function. I've basically I said that c times the argument is equals to the Green's function over c. So we lost that factor in that way, and the c has gone underneath there. Okay, multiplied by our forcing function g prime over t prime over c squared. And this thing can be simplified further. The great thing about a delta function is that if you put it on an integral sign, you simply have the value at the point at which the delta function is 0. So here we actually have two choices, and the place where the integral we're going to choose to evaluate is the t prime integral. So that will just spare us from evaluating over all the time. And simply what the delta function then does is that it says we have to evaluate the spatial integral at t prime equals to t minus c r over c. So we can now rewrite this integral, simplify it by dropping the one integration, evaluating the integration of over dt prime and losing the delta function. The minus goes out, and you have your source term evaluated over the whole domain. So you have your r prime sort of coordinates going, but the time at which you evaluate it is in the past. So you don't evaluate the forcing function at the time when you want to know it and know your solution. You evaluate the forcing function at that time minus r over c. Okay, in other words, the further the larger your radius is, the further back you have to look at where the sourcing function influences that value of r. Okay, and that kind of makes sense, because if you look at sources of waves, they take a certain speed to travel from r to the point at which they have an influence. So if you can think about it, you sort of have a sphere of influence, and you simply want to look, you combine the waves or the forcing terms from various spheres of influence at further back in time as you go further and further away from the source at which you want to evaluate it. Okay, so the second contribution is the contribution from our initial time derivative view, and I did it in this order simply because it's easier. Here we have the integral over the whole spatial domain at t prime is equals to 0. And what we then get is basically just writing it out. We have the integral over the whole spatial domain times the delta function, Now I've set t prime over there equals to 0, and I have kept this delta function in the original form. In other words, I haven't rescaled it. And the reason I haven't rescaled it is I want to make use of this delta function to get rid of the integral over r. Okay, and I can do that. And if I want to get rid of the integral over r, I want the function that multiplies r to be either plus or minus 1. Okay, so this is just this thing rewritten with our delta function substituted in. Note that here you have something in the r in the denominator that can cancel the r here that comes from the Jacobian factor or the Jacobian in the volume element. And what we then basically do is we say, once again, we can evaluate the delta function that fixes r, which is basically fixes the distance from the origin, which is now set at the point at which we want to know the solution, at which your initial condition makes a contribution. So this, while in the two-dimensional case we had an integral that focused on the furthest boundary, here we once again have the case that's very similar to the 1D case, where you actually evaluate the thing on the boundary itself. So here, what we have here is basically we want to evaluate it when r is equals to ct. Okay, so the r prime, or the source point, is basically evaluated where your r has this form. So you have r plus ct times s hat. And you're evaluating the initial conditions time derivative at this r value. So it's a fixed sphere on which you're taking the average of this initial conditions time derivative, so the average over all the possible angles, multiplied by t, okay, to give you the contribution to your u at a specific time at the point r that's the center of the coordinates or the center of the sphere. And sorry, just a quick check before I go on. You can immediately see, just as we did in the two-dimensional case, du3 dt, it will basically give you, at t equals to 0, du3 dt will basically give you your initial condition that you specified, because at t equals to 0, your r prime is just your r, so that's just your initial point. This angular average where this thing is taken out is just 4 pi, so you have exactly ut that you've specified as your initial condition. So that's just a check you have to do. The next one is the contribution from the initial value, okay, and it's slightly more complicated, just as in the two-dimensional case, because there's the t prime, the time derivative, and so I'm going to massage that until you have something that you can evaluate. And the way we do it is once again to change the integration or the differentiation of your delta function from a derivative with respect to t prime to a derivative with respect to r. Okay, so here's just the definition where I've substituted it in. Now look, if we take the derivative with respect to t prime, we basically have a factor of minus c coming out, but we don't want to do that because a delta function is nasty and the derivative is worse. So we basically switch it over. So firstly, here I've written down your delta function. I have my extra factor of minus c multiplying that one, so that's where the c squared comes in, and I'm going to evaluate it at t prime is equals to 0. Okay, so what the next, so the c squares cancel. I've put my t prime as equals to 0, and what I'm basically going to do is this prime derivative is basically equals to minus ddr of the delta function. Okay, so I can write this full term as ddr of the whole thing in brackets, where this r squared is divided by r to give you r u of r prime 0 times delta of CT minus R, okay? And then I must subtract the bit I've added in to make the full differential. And so I basically have to add back DDR of R U R prime 0 times the delta function of C minus R. And I'm very comfortable with that delta function because I can basically mean I can evaluate the integral at dr. Okay, so this first term is interesting because this is the full differential. So I simply have to evaluate it at R equals to 0 and R equals to infinity. And if you evaluate it at R equals to 0, you have a factor of R in there, so it vanishes. And if you evaluate it at R is equals to infinity, R is definitely smaller or definitely larger than CT, so this thing vanishes. So this term, the bounded term, actually contributes nothing. Okay, so you're basically left with this derivative term. And if you now evaluate, you can now expand it. So you basically have U of R prime 0 plus R, it's basically DDR of this U, which is just the gradient of U of R prime 0 dotted with S, because the DD or DDR of, where is it? That thing is basically S hat multiplied by the R that's over there. So you have this expression multiplied it by a delta function, which we can now evaluate. And that basically says we only need to evaluate this whole expression at the point where R is equals to CT. So then we get that U2, the contribution from your initial condition, is basically the averaged value, angular averaged, evaluated at a radius CT from the point at which you want to know the value of U. In this way, okay, so you basically have R prime evaluated over this average circle. This equals to CT centered at R, and what you want is you have a rough estimate of the averaged function value at this radius. And the way you do that is you take the angular average of UR plus CT times the gradient prime of R dotted with S, so the radial gradient over 4 pi. And you can see if t is equals to 0, you basically have that it is this u taken out, so it's basically u of R0 multiplied by something that's 1, and it is therefore exactly, your initial condition is then exactly encompassed here, okay, in the case where t is equals to 0. So as t grows, basically the sphere on which you work out this averaged angular estimate of u gets larger and larger, and so influences the point at R. Okay, so this is a lot of theory, and it also gives you a way of evaluating it. The only way to actually, for my personal perspective, is actually to do a specific example. And these examples are actually used a lot because the wave equation features whenever you have electromagnetism. So the example that I chose was, suppose you have an electron that oscillates up and down an antenna. Okay, so it's an ordinary straight radio antenna. It's used in every single cell phone, every single radio tower, with slightly more complicated structures than the one we're going to consider here. And let us work out what the electric potential looks like around the antenna. Okay, so work out the time-dependent electric potential psi around the antenna, and you're given that psi, or basically the wave operator of psi, is equals to minus rho of epsilon 0. And this is true for any antenna in a vacuum, which is a reasonably good approximation for the atmosphere that's not charged. Okay, and this is just a constant. Okay, and we know that rho is equals, we're going to look at the electric field for a single electron, so that's basically going to be your charge density, so it's your charge, which is a charge of electron, multiplied by a delta function, which tells you where the electron is. In other words, it's only going to be a source when R is equals to Rs. When Rs is a function of t, it's basically a vector that has a function of t that describes the position of your electron. Okay, and the delta function is also very useful because we're going to put in an integral and it makes things easier to evaluate, which is why we have the example. Okay, so Q is the charge and RS parameterizes the trajectory as a function of time. So in principle, the method I'm going to show you is entirely general up until the point at which we actually specify RS specifically. It's basically entirely general for any electron motion in three-dimensional space up until we restrict it to actually running in an antenna. Okay, and the way we're going to restrict that is we're going to say, okay, this thing just runs up and down in the z direction, so RS of t is simply sine of omega t times k. So it has basically an antenna of length 1 and it oscillates up and down in a sinusoidal manner. And we want to know what the field looks like around it. Okay, and to do this, we're going to use the method we've just designed. So we've got the Green's function that we've just used. We're going to use the initial condition psi is equal to psi t is equals to 0. And that basically means we only have to consider the first term that we used. So only the forcing term makes a contribution. And we're basically going to find that psi of r of t is equals to u1, where we described u1 in the previous slide. And we're going to use the forcing function, gr of t, is simply this function here. So here we have rho over epsilon. If you just remember from our definition of g, we basically have to multiply it with c squared because we had box of u is equals to g over c squared, just from our notation. Okay, so this is our g function. And so given that, we have that psi is equals to this integral where we've already removed the time dependence from the forcing function using the other delta function on the previous slide. And we now have a new delta function over here that we have to evaluate. And this delta function is convenient because it's going to basically mean that we formally have to integrate nothing, but we must just be careful when we evaluate it. Okay. And this, another interesting feature is we're not going to evaluate the particle's trajectory as a function of time. Remember that this t prime that enters here has actually been restricted to a thing we call the retarded time. So it lags after the time t by an amount r, which is the distance of r prime from r, which is where we want to know the solution, over c. Okay, so there's a delay between how when the electron motion affects the actual the solution at the particular point, and that delay is basically fixed by the speed of light, which gives you an indication of it's basically a wave solution where it needs a certain amount of speed for any disturbance to propagate from your source point to your field point. Okay, so now just to evaluate this thing, there's a feature of the delta functions that you may not be familiar with. So in 3 dimensions, the delta function of r minus rs is very easy. It's simply infinite at the particular point rs, and it can be written as the product of these delta functions. And if you then were to integrate over the whole volume, the particle has to be somewhere, so the integral over the whole volume is equals to 1. Okay, so now when we change coordinates to our spherical coordinates, we would like to retain the property, the probability of finding the particle somewhere is 1. Okay, and we'd also like to have these delta functions in the coordinates themselves. But when we change to non-Cartesian coordinates, there's a factor of the Jacobian coming in. So then there would be some weird, that would basically be if we did nothing, we added nothing to the delta function in the new coordinate system, basically when we evaluate it, would be the Jacobian evaluated at that specific point, which is not what we want. So if you carefully look at delta functions, you can actually see that the right way to define the delta function in a new non-Cartesian coordinate system is actually to have delta functions in the coordinates themselves divided by the Jacobian of that the square root of the determinant of the Jacobian. And that's exactly what it is. So when we transform a delta function from one coordinate system to the next, say, for example, here, we want to express the delta function r minus rs in spherical coordinates. It's a delta function of r minus rs, that's the radius, times phi minus phi s, theta minus theta s times phi minus phi s. But in order to correct for the fact that when we take the integral, we will multiplying by the square root of Jacobian, we divide by it. So when we take the integral of this thing in spherical coordinates, strictly speaking, we once again just get 1 at the point rs. Okay, and just in general, if you have a function of f from Rn to Rn, and the function is such that it's basically a coordinate change from the Cartesian coordinates x to a new set of coordinates defined by fi, then, and you define the Jacobian as just the sort of the matrix of derivatives with respect to the various new coordinates with respect to the old ones, you can then say that the delta function expressed in Cartesian coordinates is equals to the delta function in your new set of coordinates divided by the determinant, the square root of the determinant of Jacobian. Okay, so now let's use this fact to try and evaluate this integral. And I also just want to use the method again to sketch exactly what we are doing in coordinate system wise. Okay, so this is a little bit complicated, but let's look at it very carefully. Okay, so we have the antenna that is at our origin of our field coordinates. In other words, the ordinary x, y, and z. We have that the particle basically moves up and down this green line, so from 1 to minus 1 with a sinusoidal fashion. We want to know what the field, what psi is like at a particular vector r at a particular time t. And so in order to do that and to evaluate the Green's function, we say, okay, let us have a new coordinate system that is centered at r, okay, and what we care about, or what enters into the Green's function, is basically this vector r over there. Okay, so in order to evaluate our Green's function, we choose the coordinate system that we integrate over to be centered at r. Okay, so let's just write that down. And once we've chosen this coordinate system, what we basically want to do is we want to evaluate this integral over here. So this integral is basically integrating using the primed coordinate system, and what we want to integrate is this delta function of r prime minus rs. Okay, so we know in the new coordinate system we can write r prime as basically r, which is a vector in this prime coordinate system, plus r, which we, for the purposes of the integral, consider to be constant. Okay, so now let us just simply rewrite this integral as, so this delta function as a delta function on our coordinates in the prime system. So there we have that r minus this norm of r minus rs must be equal to 0. In other words, r must be such that it lies along this line, depending on what time rs is evaluated at. Theta prime must be such that r points to a point along this line, because that's the only place at which your actual argument over here of your integral is non-zero. And phi prime must be equals to phi s. Okay, and then in order to get it exactly correct that the particle is somewhere, we add this factor of r squared over sine prime. Okay, so this is what this three-dimensional delta function factor actually becomes in terms of coordinates. So when we do that, evaluating this thing becomes amazingly simple, because the sine phi prime and r squared term basically vanishes, okay, and we're just left with a whole bunch of delta functions over r that we have to evaluate. Okay, so just phi s, and the beauty is we don't actually need this information, but just to get, because I had to draw the picture, I had to compute it. So phi s is equals to 2 pi minus phi. Okay, so here's your phi, and the phi that indicates your big R vector is just 2 pi minus phi of your red R vector. Your psi s, or theta s, is equals to, which is basically this angle. You can compute using the cosine rule, and that's basically, you get the sine of theta over r is equals to this angle over little r. Okay, so the arc sine and then pi minus to get that angle over there. So that's just the geometry. And if you have these two, and you then have r restricted to r minus rs, you actually get a very simple expression for your psi. It is simply this factor that's only dependent on r. Okay, so you basically have q over epsilon 0 4 pi r, but there's a catch. Okay, the place at which you evaluate r, if you look at it over here, is dependent on r prime that we know lies along here. It basically is the point at which you have the electron, so it's basically equals to rs. So we have that r is equals to this norm, so it's basically r minus sine of omega t prime. Okay, so it's basically r minus r prime, the only place at which the forcing function is non-zero. But this r prime is moving up and down this antenna, or this antenna over here. Okay, and this is tricky because your r is where you evaluate psi is implicitly dependent on t prime, but t prime is, remember, t minus r over c. Okay. So while this expression looks quite simple in respect to r, it's quite hard to get what r actually is for a specific time, because this definition of r is implicit. Okay. So one way of evaluating this, and to just get an estimate when you are working with this type of problem, is to look at it, what happens when you are far away from the antenna. So when you're far away from the antenna, what we're going to do is basically try and make an expansion in terms of the actual position where you want to know your electric potential's value. And the way we do that is to use our cosine rule. Okay, so we can write down what r is in terms of r and the position that you are on the antenna, even though you don't know exactly what that position is, and you just use your cosine rule. So it's just r squared plus r prime squared minus 2r prime times cos theta, where theta is that angle. Okay, and what you can now say is, if this r is much, much larger than basically rs, which is 1, which is for this case, which is the maximum value of the range where your particle moves, what you can then do is simply find an expression for r over r prime, which is just the square root of 1 minus 2 times rs over r plus r squared, to a linear order. Okay, so that's basically 1 minus rs over r cos phi. And then you can write r over r prime, so you can find the inverse and you can substitute it in there. And it's easy to know what r is, because r is just where you're evaluating your function psi, and then you can see what the rest of the contribution is like. So let's just do this in detail. So you have that r over r prime is equals to this, and that means that little r over big R becomes 1 plus rs over r times cos theta, and rs is simply just minus sine of omega t prime. So if you substitute that back into expression for psi, you simply replace r with 1 over r by 1 over little r times by 1 plus cos of theta over r sine of omega evaluated at t minus r over c, where you've replaced r with its first estimate. So that's just little r over c. Okay, and so this gives you a formula far away from this antenna of what your field will be like. And what you can notice a number of things. The first one is the field changes with the same frequency your source changes, okay, which you can be expected because it's just a linear wave that you're sending out. But the time at which the source's influence appears at a specific field point over here is delayed by r over c. In other words, the distance at the field point is on average from your antenna is the sort of delay of the source point over here. And another interesting thing is there is an angular dependence on the antenna. In other words, when cos theta is equals to 0, in other words, if you're on this y in the xy plane, then the amplitude of your field variations is going to be a maximum. In other words, your signal will be the strongest. If however cos theta is pi over 2, in other words, your field point sits over here, then you're going to have no time variation in your signal. In other words, you're going to have a very, very weak signal. And this is one of the flaws of just having a linear antenna up and down like this, is that your reception is basically dependent on angle. And that's the reason why even in the television, for a television, your antenna have little bunny ears, and some of your other antennas have a series of these sort of linear antennas, if that's how it's been built, so that this cos, you then have various signals going out with various angles, so that there's at no point where your signal completely vanishes, like this antenna example that we've done here. So there's a tremendous amount you can actually learn by simply looking at the far field approximation of your solution. Okay, so I hope this helped clarifies how you can use Green's functions to look at electromagnetic radiation, as well as the way to derive the Green's function for 3D. And I might comment that this is possibly in electromagnetism, most of our designs of antennas is actually comes and radio waves and cell phones and things was actually developed just simply using this Green's function and evaluating it in various limits. So it's a very, very useful piece of mathematics that's been used well from the development of radar till now in an incredible number of ways.